Well, hello everybody. What I need to do with you today is I need to cover section 8-3, which is over convergent and divergent sequences. The other things that happened in class today, we did answer questions over section 8-1 and 2, and then we did do a homework quiz on that. So you need to make sure that you get in and get that caught up for us. Then, of course, we'll end with an assignment. So what you'll need in front of you is you'll need your Day 2 class examples that says FST Lesson 8-3 Limits. Now, some things that you're going to hear today. You're going to hear the word convergent. The word convergent means that you approach something. In this case, it means that we're going to approach some number. So you're going to be given a sequence from section 8-1 and 2, and then as you allow n to go to infinity, we're going to approach some number. And I'll show you what I mean there. You will also see the term divergent. Divergent means just the opposite. It does not approach a number. It goes on forever, so it approaches either infinity or negative infinity. You'll also hear the word discrete, which we touched on last class. The word discrete means you're only dealing with integers. 1, 2, 3, 4, 5. So when you graph a discrete function, you do not connect the dots because there's no decimals in between. So if you would, come over to your number 1. I'm going to give you the sequence that says b sub n is equal to negative 2n, and what I'd like to do is list the first 5 terms. Well, little things that I know about this. This is a geometric sequence. As I plug in 1, my first term is negative 2. When I plug in 2, I've got negative 4. When I plug in 3, I've got negative 6, negative 8, and negative 10. Now, let's graph these as a discrete function. And here's what I mean by that. The value of the first term is negative 2. The value of the second term is negative 4. We're not going to connect the dots because we don't have a 1.1 term. We don't have a 1.8 term. The value of the third term is negative 6. The value of the fourth term is negative 8. And the value of the fifth term is negative 10. Look at what's happening to your y values. As my x values grow, 6, 7, 8, 9, 10, 100, 1,000, my y values are going to continue to decrease. Notice that this is just going to go down forever. This is called a divergent function. Because it does not approach a number, it grows, or in this case shrinks, forever. So this is divergent. In this case, I'm going to say the limit does not exist because we do not approach a number. So that's all I've got on the first one. Let's look at your second one and see what happens. I'm going to give you the sequence that says C of n is 1 over n. So let's plug in 1, then 2, then 3, then 4, then 5 to get our values. So the value of the first term, so to get C of 1, I'm going to plug in 1. 1 over 1 is 1. Now let's go get the second term, so C of 2. Plug in a 2 and I'm at 1/2. Let's find C of 3, 1/3. C of 4, 1/4. And of course C of 5, 1/5. Notice what these numbers are doing. They continue to get smaller and smaller and smaller. If I look at it graphically, the value of my first term was 1. The value of my second term was 1/2. The value of my third term was 1/3. The value of my fourth term was 1/4, which is less than 1/3. And then the value of the fifth term, of course, 1/5, less than 1/6. So look at what's happening. Now, let's look ahead a little bit. Let's pretend that way out here I'm at the 100th term. Well, its value would be 1/100th. Notice that I did not cross the x-axis. So we're not going to connect the dots on this graph, but look at the pattern of what's happening. It behaves like an exponential function. It's going to get really, really, really close to 0, but it's never going to touch 0. Think about 1,000, a million. So when I look at how this thing's behaving to the right, I'm going to say that the limit of the function of c of n is 0, because my numbers keep getting smaller and smaller and smaller. Now, any time that you have a numerator that's greater than the denominator, let me say that again, anytime you have a numerator that's less than the denominator, you'll always approach 0. I've got a couple more coming in there for you. So jump over to your number 3. The limit as n approaches infinity of 1/n equals 0. Now, this n approaches infinity means you're going to do this forever. 1, 2, 3, 4, 5, 10, 20, 100, 1,000, a million. So it's going to resemble the graph that we just did right here. Here's the graph of 1/n. But instead of stopping at 5 or 100, I'm going to go to 1,000. So guys, I want you to notice this. Any time that the degree of your numerator, this is a really important statement, any time that the degree of your denominator is higher than the degree of your numerator, your limit will always be 0. So down the road, if I ask you the limit of 5/n, the biggest power is in the denominator, that's going to go to 0. If I ask you -3/n, the biggest power is in the denominator, so it's also going to approach 0. So there's one of our main formulas. The limit as n approaches infinity of 1/n is going to be 0. Now, think about this graph. It looks like this. Anytime there is a limit, you're going to get what we call a horizontal asymptote. In this case, my y values continue to shrink, but they will never ever touch the x-axis. In this case, I have a horizontal asymptote at y equal 0. So I'm going to say that the limit as n approaches infinity of 1/n is 0. That's equivalent to having a horizontal asymptote of y equals 0. Now, come over to your alternating sequence, the alternating harmonic sequence. I've already plugged in 1 for you, at n2, at n3, at n4, at n5. What I'd like to do is look at the graph and see if it seems to approach a number. So when I plugged in 1, I went -1 to the first over 1. That's where I got -1. Now let's plug in 2. I've got -1 squared over 2. Well, -1 squared was 1 over 2. So you can kind of see where I've got the numbers. Let's graph this and see what it looks like. So it looks like I need to cover -1. So let's come down here at -1. That means I'm going to come up here at 1. Now, the value of my first term is -1. Now, in a different color, I'm going to graph my second term. The value of my second term is 1/2. Let me come back to black. The value of my third term is -1/3. So what do you think, right in there? The value of my fourth term is +1/4. The value of my fifth term is -1/5. The value of my sixth term is going to be +1/6. We'll look at how your graphs are behaving. Down here, they're doing like this. Up here, they're doing like this. So ask yourself, does it seem like we're approaching a number? And in this case, my values continue to get smaller and smaller and smaller. So I'm going to say this, the limit as n approaches infinity of d of n, that happened to be the name of our function, continues to get smaller and smaller and smaller. It approaches the x-axis. So I'm going to say that that limit is 0. So you're looking at the y value that we approach. Let's look at your number 4. I'm going to give you 2n plus 1 over n. To get the value of your first term, you're going to plug in 1. So e of 1 would be 2 times 1 is 2, plus 1 is 3 over 1. That's where I got that. To get the second term, plug in 2. 2 times 2 is 4, plus 1 is 5 over 2. So that's where we generated these numbers. Now, let's picture this. There's a 1, there's a 2, there's a 3. Now, let's plot these and see if we can figure out anything. And then I'm going to come back and have you relook at the equation. The value of the first term was 3. The value of my second term was 2.5. The value of my third term was 7/3, which is 2 1/3, so 2.33333. The value of my fourth term is 9/4, which is 2.25. The value of my fifth term was 11/5, which was 2.2. So we need to try to decide what this thing's approaching. Ask yourself real fast, is it approaching 0 in this case? And the answer is going to be no. If you see it, it's approaching 2. Now let me show you this. Let's reduce 2n plus 1 over n. I can think of that as 2n over n plus 1 over n. If I reduce that, 2n over n is 2 plus 1 over n. Well, we know from our previous example, this limit right there is 0. So I have 2 plus 0. So the answer to this, the limit as n approaches infinity of e sub n, in this case is going to be 2. You will never ever go below 2 in this example. So what I did first is reduced it, and if you get a constant, that's going to be your answer. Since I just said that, now let's look at our example 5. F of n is 2. So it means the value of my first term is 2. The value of my second term is 2. The value of my third term is 2. So it's going to look like this. The value of my first term is 2. The value of my second term is also 2. The value of my third term is also 2. This limit, since this is a constant, is 2. So I'm going to say that the limit as n approaches infinity of f of n is 2. Quick moral of that story, whenever you have a constant, that is your answer. Let's look at number 6. The limit of g sub n as 2 over n. Well, we can pick some points, but I'm going to throw this out. Look at where your highest power is. In the top, since there's no n, it's really n to the 0. In the bottom, it's n to the first. Since my highest power is in the denominator, this is going to have a limit of 0. To show you graphically, when I pick on my first term, when I plug in a 1, I'm going to get a value of 2. When I plug in 2, 2 divided by 2 is 1. When I plug in 3, I'm going to get 2/3. When I plug in 4, I'm going to get 2/4, so I'm going to get 1/2. Let's jump way out here to 4, 5, 6, 7, 8, 9, 10. When I plug in 10, 2/10 is 1/5. Now think ahead a little bit. What if you did 100, 1,000, 1,000,000? You're still going to be a little bit above that. So I'm going to say that the limit of g sub n, let's say that again, the limit as n approaches infinity of g sub n in this case is 0. 0 because my highest power was in the denominator. Now, you should also have a note card in front of you. If not, make sure you ask us for that note card. But you should have a note card that has some information on there that I'm going to explain here real fast. This looks really, really complicated, but here's all it says. If you're trying to find the limit of some constant, which our book decides to call k instead of c, that is your answer. If you have the limit of something plus the constant, your answer is whatever that constant is plus that limit. And I'm going to do a couple of those examples for you on that back page. Now, here's your note card material. The important things that I need you to know out of this would be this. There's 3 scenarios that's going to happen whenever you're looking for the limit. On the top one here it says this: if the degree of the numerator is less than the degree of the denominator. We've already done a couple of those, like 1 over n, 2 over n. Whenever the degree of the numerator is less than the degree of the denominator, your limit will always be 0. And that's said to be convergent. So now, just an example that we haven't looked at. If you look at an example like this, x over x squared plus 1, the highest power is in the denominator. So this thing will have a limit of 0 as x goes larger and larger and larger. If you have a expression where the power of the numerator is equal to the power of the denominator, you just look at those coefficients. So in this case, it's going to be convergent, and it's going to converge to the number 3/4. Here's another one. Let's say I give you 5x squared plus 7x minus 11 over 8x squared minus 3x plus 4. What you do is you look at the powers of the leading coefficient. The highest coefficient on the top is a 5, and we get that from the x squared. The leading coefficient in the denominator is 5/8. Now look at the powers. They're both a squared. So this thing is going to approach the number 5/8 as x gets larger and larger and larger. The third scenario you're going to see is the scenario when your numerator power is greater than your denominator power. That'll be our case number 3. Notice that the highest power is in the numerator. Whenever the highest power in the numerator, it's going to be divergent. And it's either going to approach infinity or negative infinity. Depends on what the equation looks like. Now, while I got you a little confused, come over to your back page and I'm going to talk you through those real fast. I'm going to give you the sequence. Here's your number 1. I'm going to give you the sequence where it's the constant term of 9.8. Now, on this worksheet, we're going to say, does it converge or diverge? and then we're going to state the limit. Now, in this case, since this is a constant term, that is your answer. So my number 1, this sequence converges. This sequence converges. The first term is 9.8, the second term is 9.8, the third term is 9.8. So I'm going to say that the limit is 9.8 because that's all it is ever. Let's look at your number 2. Here's how to attack this. Look at your powers. Go find your highest power in your numerator, your highest power in the denominator. The highest power in the numerator is to the first. The highest power in the denominator is to the first. Now, look at the leading coefficients of that part. So you can ignore that. You can ignore that. Look at this part right there. And that's going to be your answer. So in this case, this converges. And it has a limit of -1 over -3, which is 1/3. Here's my number 3. I've got n squared over 2n plus 100. Go find your highest powers. The highest power in the numerator is a squared. The highest power in the denominator is a 1. Since the highest power in the numerator is bigger than the highest power in the denominator, this thing's divergent. So the limit does not exist. It means it either goes to infinity or negative infinity. So the highest power in the numerator does not exist. Here's my number 4. Let's look at this one because one power's at n and the other's at n squared. So let's list a couple of terms to see if we can get a feel for this. Let me plug in a 1 to get the value of the first term. I'm going to have -1 to the first, which is -1 over 1 squared. So my first term is -1. Now let's plug in a 2. -1 squared is a 2. -1 squared is a 1. Must be getting late. Over a 2 squared is a 4. So my second term is a 1/4. Now let's plug in a 3. -1 cubed is -1. 3 squared is 9. One more. Let's plug in a 4. -1 to the 4th is 1. 4 squared is 16. Well, look at what these numbers are doing. Number 1, they are alternating. Positive, negative. But look at what they're doing. I'm going from -1 to -1/9. I'm going to 1/4 to 1/16. So I'm getting smaller and smaller and smaller. So this sequence is convergent. And my limit is approaching 0. Here's my last couple. My number 5, 6n plus 4 over 5n, or 5 minus 3n. Number 1, go find your highest power. The highest power in the numerator is to the first. The highest power in the denominator is also to the first. So that means this thing is going to converge. Now let's go figure out the limit. So look at the coefficients of that part. So I'm going to look at the coefficients right there, guys. Look at the coefficients of 6n over -3n. Look at 6 divided by -3. This has a limit of -2. Here goes your number 6. Like to find the limit of that. Now, since there's a constant involved, my limit is at least 3. My limit is at least 3. Now, let's look at 1 over 6n. The highest power is in your denominator. Whenever your highest power is in the denominator, this part has a limit of 0. So I'm going to have 3 minus 0. So this sequence converges and also has a limit of 3. See if you can get a jump start on me on number 7. Peek at your powers real fast and see if you can decide what that limit might be. Hint, hint, there is a limit. So here goes thinking. Go find your highest power. They are both a squared. That means this doesn't count, this doesn't count, that doesn't count. So I'm focusing on the 5n squared over the 2n squared. Since the powers are the same, this converges for sure. Look at the coefficients, and I'm going to get 5/2. So this has a limit of 5/2. It also means, guys, if we graph it, I have a horizontal asymptote at y equal 5/2. If there's a limit, there's a horizontal asymptote. Here goes my last one. We're going to tell you that the very first term is 10. The next term can be found by -2 times the previous term. So this is a recursive formula. So I'm going to have 10 for my first term. To get my second term, I'm going to multiply my first term by -2 and get -20. Let's multiply by -2 again and get 40. -80, 160. What do these numbers seem to be doing? They're alternating, but I'm going to go from 10 to 40 to 160, -20 to -80. So I'm not approaching a number. So this would be divergent. And the limit in this case does not exist. So guys, if you do not have that note card, stop by and let us put that in your hand. But even if you don't have that note card, you really don't need it. You got 3 cases. Case number 1, if your higher power is in the denominator, your limit is automatically 0. If the highest power in the numerator is the same as the highest power in the denominator, you go find those coefficients. Here's a real quick example. 5x squared minus 8x plus 11 over 12 plus 11x squared minus 6x. I purposely mixed them up, but the highest power in both of them is a squared, so go find those. This has a limit of 5/11. The third and last scenario is if the biggest power is in the numerator. If that happens, it's divergent. It means it's either approaching infinity or negative infinity, or even both. So, guys, you should have the day 2 assignment. Good luck on it. Come in if you have any questions.